We are all familiar with the three basic states of matter: solid, liquid, and gas. However, there exists a fourth state, a state far more prevalent in the universe than the other three combined. This state is called plasma, and it is essentially a gas that carries an electrical charge. Plasma is formed when atoms, subjected to intense heat or other forms of energy, lose some or all of their electrons. Stars, those celestial giants that illuminate the cosmos, are essentially giant balls of plasma. The auroras that dance across our planet's poles, captivating observers with their ethereal beauty, are also examples of plasma in action. Plasma's significance extends far beyond its celestial manifestations. From the fluorescent lights that illuminate our homes and offices to the intricate etching processes used in microchip manufacturing, plasma technology has seamlessly interwoven itself into the fabric of our lives. Understanding plasma is not just about unraveling the mysteries of the universe, it's about harnessing its immense potential to address some of the most pressing challenges facing humanity. As we delve deeper into the realm of plasma physics, we embark on a journey that promises to unlock groundbreaking technologies and shape the future of our world. For centuries, humanity has looked to the sun as a source of life-giving energy. Now scientists are working tirelessly to replicate the sun's power here on Earth through a process called controlled thermonuclear fusion. Fusion, the process that powers the sun and other stars, involves fusing together light atomic nuclei to create heavier ones, releasing tremendous amounts of energy in the process. One of the most promising fusion reactions for energy production is the deuterium-tritium (DT) reaction. Deuterium can be extracted from seawater, while tritium can be produced from lithium, a readily available metal. This abundance of fuel makes DT fusion a highly attractive option for a sustainable energy future. The DT fusion reaction involves fusing a deuterium nucleus with a tritium nucleus to create a helium nucleus and a highly energetic neutron. This neutron carries away the majority of the energy released in the reaction, which can then be harnessed to generate electricity. Controlled fusion holds the promise of a clean, safe, and virtually limitless energy source. With its potential to revolutionize the global energy landscape, controlled fusion stands as a beacon of hope for a sustainable future. Achieving fusion is no easy feat. Atomic nuclei are positively charged, and like charges repel each other. To overcome this electrostatic repulsion, known as the Coulomb barrier, the nuclei must be brought incredibly close together, essentially forcing them to fuse. This requires immense temperatures and pressures, conditions found naturally in the cores of stars but extremely challenging to replicate on Earth. Imagine trying to bring two magnets together with their like poles facing each other. The closer you bring them, the stronger the repulsive force becomes. Overcoming this repulsion requires a significant amount of energy. The same principle applies to atomic nuclei. To overcome the Coulomb barrier and achieve fusion, the nuclei must be moving at incredibly high speeds. This translates to temperatures of millions of degrees Celsius, hotter than the core of the sun. Achieving and maintaining such extreme temperatures is one of the biggest challenges in fusion research. Scientists are developing innovative methods to confine and heat plasma, using powerful magnetic fields and lasers to achieve the conditions necessary for fusion. In the quest for practical fusion energy, the Lawson criterion, formulated by British physicist John Lawson in 1955, serves as a critical benchmark. This criterion outlines the conditions necessary to achieve ignition, the point at which a fusion reaction becomes self-sustaining, producing more energy than it consumes. The Lawson criterion essentially boils down to two key parameters: temperature and confinement time. Temperature refers to the kinetic energy of the plasma particles, which must be high enough to overcome the Coulomb barrier and initiate fusion reactions. Confinement time, on the other hand, refers to the duration for which the plasma can be maintained at the required density and temperature. The product of plasma density, confinement time, and temperature must exceed a certain threshold for ignition to occur. Achieving these conditions simultaneously has proven to be an immense technological challenge. However, significant progress has been made in recent years, with experimental fusion reactors coming closer and closer to achieving the elusive goal of ignition. Section 5. Confinement, trapping plasma's fiery power. Confining plasma, a swirling mass of charged particles heated to millions of degrees, presents a formidable challenge. Conventional containers simply melt away when exposed to such extreme temperatures. To overcome this obstacle, scientists have devised ingenious methods to trap and manipulate plasma, effectively holding the key to unlocking fusion energy. Magnetic confinement, one of the most promising approaches, utilizes powerful magnetic fields to confine the plasma. These fields act as invisible walls, guiding the charged particles along specific paths and preventing them from coming into contact with the reactor walls. Tokamaks, donut-shaped devices, and stellarators, twisted ring-shaped devices, are two prominent examples of magnetic confinement fusion reactors. Inertial confinement, an alternative approach, relies on intense laser beams or particle beams to compress and heat a tiny pellet of fusion fuel. The beams strike the pellet from all sides simultaneously, causing it to implode inward, creating the extreme temperatures and pressures required for fusion. This implosion happens incredibly fast, on the order of nanoseconds, hence the term inertial confinement. Electrostatic confinement, a lesser-known but intriguing approach, uses electric fields to confine the plasma. These fields, generated by electrodes within a vacuum chamber, can trap ions and electrons, creating a region of high plasma density. While still in its early stages of development, electrostatic confinement offers potential advantages in terms of simplicity and scalability. Each confinement method has its own set of advantages and challenges. The quest for the optimal confinement method continues, driving innovation and pushing the boundaries of plasma physics. Section 6. Magnetohydrodynamics, harnessing plasma for power generation. Magnetohydrodynamics, a fascinating field that explores the interaction between electrically conducting fluids, such as plasmas and magnetic fields, offers a unique pathway for power generation. MHD generators, unlike traditional generators that rely on rotating machinery, directly convert the kinetic energy of a flowing plasma into electricity, promising higher efficiencies and reduced environmental impact. The basic principle behind MHD power generation is elegantly simple, yet incredibly powerful. A plasma, created by heating a gas to high temperatures, is passed through a channel permeated by a strong magnetic field. As the charged particles in the plasma move through the magnetic field, they experience a force perpendicular to both their velocity and the magnetic field lines. This force, known as the Lorentz force, drives the charged particles towards electrodes placed on opposite sides of the channel, inducing an electric current. MHD generators offer several advantages over conventional power generation technologies. They operate without any moving parts, eliminating the wear and tear associated with rotating machinery and potentially leading to higher reliability and lower maintenance requirements. While MHD power generation holds immense promise, several challenges remain before it can be widely deployed. Section 7. Plasma propulsion, charting a course to the stars. As we set our sights on the cosmos, dreaming of exploring distant planets and unraveling the mysteries of the universe, the limitations of conventional chemical rockets become glaringly apparent. Plasma propulsion, a revolutionary technology that harnesses the power of plasma to propel spacecraft, offers a tantalizing glimpse into a future where humanity can venture farther and faster into the cosmos. Plasma thrusters, the workhorses of plasma propulsion systems, utilize electric fields to accelerate ions, creating thrust. These thrusters, unlike chemical rockets that produce thrust through the violent combustion of propellants, generate a gentle but continuous thrust, allowing spacecraft to accelerate gradually over long periods of time, reaching speeds unattainable by chemical rockets. Plasma propulsion offers several key advantages over chemical propulsion. Plasma thrusters are incredibly fuel efficient, requiring significantly less propellant than chemical rockets to achieve the same change in velocity, a crucial factor for long-duration space missions. Plasma thrusters can achieve much higher exhaust velocities than chemical rockets, enabling spacecraft to travel much faster, potentially reducing mission durations from years to months or even weeks. Plasma propulsion systems are highly scalable, ranging in size from miniature thrusters used for precise satellite maneuvering to larger thrusters capable of propelling crewed spacecraft to Mars and beyond. While still in its early stages of development, plasma propulsion has already made its mark on space exploration. As research and development continue, plasma propulsion is poised to revolutionize space travel, enabling humanity to explore the cosmos like never before. Section 8. Plasma Physics, a gateway to technological marvels. Plasma physics, the study of the fourth state of matter, stands as a testament to humanity's insatiable curiosity and unwavering pursuit of knowledge. From the depths of space to the heart of fusion reactors, plasma, a swirling mass of charged particles, captivates our imagination and fuels our technological aspirations. As we delve deeper into the intricacies of plasma behavior, we unlock a treasure trove of potential applications that promise to revolutionize various aspects of our world. Controlled fusion, the holy grail of energy production, beckons us with the promise of a clean, safe, and virtually limitless energy source. Imagine a world where energy scarcity becomes a distant memory, where greenhouse gas emissions plummet, and where the scourge of energy poverty fades into oblivion. Plasma physics holds the key to unlocking this transformative technology, paving the way for a sustainable energy future. Plasma propulsion, with its promise of faster and more efficient space travel, ignites our dreams of exploring the cosmos. Imagine a future where humanity ventures beyond the confines of Earth, establishing outposts on the Moon, sending crewed missions to Mars, and perhaps even embarking on interstellar voyages to distant star systems. Plasma technologies have already found their way into our daily lives, from the fluorescent lights that illuminate our homes, to the advanced manufacturing processes that produce our smartphones and computers. As our understanding of plasma deepens, we can expect to see even more innovative applications emerge, impacting fields as diverse as medicine, agriculture, and environmental remediation. As we continue to unravel the mysteries of plasma, we embark on a journey of discovery and innovation that will undoubtedly shape the future of our world and beyond. Imagine a world where we can generate electricity without turbines or spinning parts. A world where the very forces that govern the stars could power our homes and propel us through the cosmos. This is the promise of Magnetohydrodynamics, or MHD for short. It's a field that explores the fascinating interplay between electrically conductive fluids, like plasmas and liquid metals, and powerful magnetic fields. At its heart, MHD is about harnessing the power of moving charges. When a conductor, carrying an electric current, moves through a magnetic field, it experiences a force. This force, known as the Lorentz force, is what drives electric motors, generates electricity in generators, and even influences the behavior of plasmas in stars. MHD takes these fundamental principles and applies them to a fascinating class of fluids, plasmas. Often called the fourth state of matter, plasmas are gases that have been energized to the point where their atoms lose some electrons, becoming electrically charged. This unique property allows plasmas to interact with magnetic fields in ways that ordinary fluids cannot. By understanding and manipulating these interactions, MHD opens up a world of possibilities. From generating clean energy to propelling spacecraft to distant planets, MHD promises to revolutionize our technological landscape. It's a field where scientific curiosity and engineering ingenuity converge, offering a glimpse into a future powered by the very forces that shape our universe. One of the most compelling aspects of MHD is its inherent simplicity. Unlike traditional power plants that rely on complex mechanical systems with turbines and rotating parts, MHD generators operate on a more elegant principle. They directly convert the kinetic energy of a conductive fluid into electricity. bypassing the need for any moving mechanical components. This simplicity translates into several key advantages. First, it enhances reliability. With fewer moving parts to wear out or break down, MHD generators promise increased durability and reduced maintenance requirements. This makes them particularly attractive for applications requiring high reliability, such as power generation in remote areas or during emergency situations. Second, MHD generation boasts high efficiency. Traditional power plants lose a significant portion of energy as heat during the conversion process. MHD systems, due to their direct energy conversion, minimize these losses, leading to more efficient energy production. This translates into reduced fuel consumption and lower environmental impact. Finally, MHD offers the potential for cost-effectiveness. While the initial investment in MHD technology might be comparable to traditional systems, the long-term operational costs are expected to be lower. This is due to reduced maintenance, higher efficiency, and the potential for using a wider range of fuels, including those considered unconventional. For centuries, humanity has gazed at the stars, yearning to explore the vast expanse beyond our planet. While chemical rockets have taken us to the moon and beyond, their limitations become apparent when we set our sights on more distant destinations. This is where plasma propulsion, a revolutionary technology rooted in MHD principles, enters the picture. Imagine spacecraft that glide silently through the void, propelled by glowing plumes of plasma. These spacecraft, equipped with plasma thrusters, hold the key to unlocking the solar system and beyond. Unlike chemical rockets that burn fuel in short, powerful bursts, plasma thrusters generate thrust by accelerating a stream of charged particles or plasma using electric and magnetic fields. Plasma propulsion offers several advantages over conventional chemical rockets. First, it boasts significantly higher fuel efficiency. Since plasma thrusters can achieve much higher exhaust velocities, they require far less propellant mass to generate the same amount of thrust. This translates to lighter spacecraft, longer mission durations, and the ability to reach distant celestial bodies within a human lifetime. Moreover, plasma thrusters offer the potential for continuous acceleration. Unlike chemical rockets that fire in short bursts, plasma thrusters can operate continuously for extended periods, gradually increasing the spacecraft's velocity. This constant acceleration allows for faster travel times and opens up new possibilities for exploring the cosmos. Section 4. Igniting the cosmic engine, how plasma thrusters work. The heart of a plasma thruster is a chamber where a neutral gas, typically xenon or argon, is injected and ionized to create a plasma. This plasma, now a swirling sea of charged particles, is then subjected to powerful electric and magnetic fields. These fields are carefully configured to accelerate the plasma out of the thruster at incredibly high speeds, generating thrust. Different types of plasma thrusters achieve this acceleration in unique ways. One prominent type, called the Hall thruster, utilizes a crossed electric and magnetic field configuration to trap electrons within the thruster. These trapped electrons then collide with the neutral gas atoms, ionizing them and creating the plasma. The electric field then accelerates this plasma, generating thrust. Another type, the Magnetohydrodynamic (MPD) thruster, utilizes the interaction between a high current flowing through the plasma and its own induced magnetic field to generate thrust. This interaction creates a powerful electromagnetic force that accelerates the plasma to extremely high velocities, making MPD thrusters suitable for high-power, high-thrust applications. Regardless of the specific type, all plasma thrusters share a common thread. They harness the power of electromagnetism to control and accelerate plasma, generating thrust and propelling spacecraft silently through the vast expanse of space. Section 5. Taming the Star Within, Challenges in Plasma Propulsion. While plasma propulsion holds immense promise for space exploration, it also presents unique challenges. One of the most significant hurdles is the high temperatures involved. Plasma, by its very nature, exists at extremely high temperatures, often reaching tens of thousands of degrees Celsius. Containing and manipulating such a hot and energetic substance requires advanced materials and engineering ingenuity. Another challenge lies in the efficient generation and control of the powerful magnetic fields required for plasma confinement and acceleration. These fields need to be strong enough to contain the plasma, yet flexible enough to allow for precise control of its flow. Achieving this delicate balance necessitates sophisticated magnet design and power management systems. Furthermore, the power requirements for plasma thrusters can be substantial, especially for high-thrust applications. While solar panels can provide sufficient power for some missions, more ambitious voyages might require alternative power sources, such as nuclear reactors, which introduce their own complexities and safety considerations. Despite these challenges, scientists and engineers around the world are continuously pushing the boundaries of plasma propulsion. New materials, innovative designs, and advancements in power generation are paving the way for a future where plasma-powered spacecraft become a common sight, venturing further and faster into the cosmos. Section 6. Reflecting on the stars. Key takeaways from our exploration. Our journey into the world of MHD and plasma propulsion has revealed a universe teeming with possibilities. We've delved into the fundamental principles that govern the interaction between electrically conductive fluids and magnetic fields, witnessing how these interactions can be harnessed to generate clean energy and propel spacecraft to distant stars. We've explored the allure of MHD's simplicity, discovering its potential for enhanced reliability, increased efficiency, and reduced costs. We've ventured into the realm of plasma propulsion, envisioning spacecraft gliding silently through the cosmos, powered by glowing plumes of plasma. Yet, our journey has also highlighted the challenges that lie ahead. From containing and controlling superheated plasma to generating powerful magnetic fields and addressing power requirements, each obstacle presents an opportunity for innovation and scientific discovery. Section 7. Keep looking up, a final word and invitation to explore. As we stand on the cusp of a new era in space exploration, MHD and plasma propulsion beckon us to dream bigger, to push the boundaries of what's possible. They offer a glimpse into a future where humanity ventures beyond Earth, not just as explorers, but as a species capable of navigating the cosmos with grace and sustainability. But this journey is not just for scientists and engineers. It's a journey for all of us. So, the next time you gaze up at the night sky, let your curiosity soar. Let the twinkling stars ignite your imagination and inspire you to learn more about the fascinating world of MHD and plasma propulsion. The universe awaits, and together, we can unlock its secrets.
Am I the only one that didn't know just how much effort goes into our channels? Let's talk about that. At the Salah Lotfy Channel for Science, we're diving deep into the wonders of plasma. For this journey, we owe a huge thank you to Professor Dr. Tarek Nagla, whose expertise and passion light up every episode. Thank you, Dr. Nagla, for your unwavering support and invaluable knowledge. You make science not just understandable, but truly exciting. And to our amazing followers, your curiosity fuels us. We appreciate each comment, like, and share. Got thoughts on this episode? Drop them below. Here's to learning and exploring together. Thank you, everyone.